Can you hear me okay? All right, thank you. Yeah, so I got asked to give a public talk here, and I've given a few public talks before, but one thing that always happens in public talks, how many of you are actually members of the public as opposed to being a mathematician? Right, so it's kind of almost nobody, right? So public talks tend to be you pretending to be the public and me pretending to talk to the public, and it's kind of, I don't know, dishonest or something. But I wanted to take this occasion to kind of collect some things that I've thought about and experienced giving public talks and talk about giving a public talk. I think it's important that we address the public and that we convey what mathematicians do and what mathematics is about to the public. And I think it's somehow particularly important in this era. So that's why I called this A Mathematician Goes Out in Public. And when a mathematician goes out in public, this is usually the kind of thing people think will happen. That mathematicians are kind of nerdy, we take things too literally, and we probably get it wrong. We think we understand how something works, we've got some technical expertise, and we just direct it straight at the problem. And in fact, something like this happened to me. Maybe this is a typical thing. That's a picture of a corner in a house and a corner shelf. And I needed to have a corner shelf somewhere. It was actually in an outdoor space on the house. And I knew if I did it myself, I would spend a long time researching just what kind of wood to use, just what kind of finish to go on that wood to withstand the rain. I would probably discover all kinds of things about home building. It would just become a whole research project. So I hired a contractor and a carpenter to do it. And the guy came over, and I told him how high he wanted it, and I wanted it, and he had to leave, and he goes, okay, well, just tell me how long you want that long side to be. And I really tried, you know. I'm a mathematician, and in my head, I'm driving in a car and down a mountain road, and like the brakes are out, and I'm going faster and faster, and the end of that road is my mouth, and I just can't stop myself, and I say, you mean the hypotenuse? And he goes, yeah, whatever, just give me the number. So it's difficult. It's not easy going out in public as a mathematician or even just interacting with people. And in fact, one of the scenes that captured that feeling the most was a scene from Napoleon Dynamite. I actually was going to show the thing on YouTube, but I don't know. I wasn't sure I was allowed to show YouTube videos here. Anyway, there's a scene where Napoleon Dynamite's going to work on a chicken farm, and they have to do something there. And he says to the farmer, do the chickens have large talons? And the farmer says, oh, I lost it. No. And he says, what? And he says, do the chickens have large talons? And the farmer says, I don't understand a word you just said. So this is also kind of the typical thing that I feel. You have some kind of expertise, some kind of technical knowledge. Maybe you know a few of the technical words, and you go out and you just get in trouble using them the wrong way. Okay, so how do we convey like what this is we do, the kind of people we are, and the things we love about math? And there's a lot of different ways people do it, and there's a lot of ways I've heard since I've been here of people doing it. There's amazing things people are putting out on the web for people to engage with in mathematics. We heard a lot of those last week. Anyway, there's some, I'm sorry, I forgot I wrote some names down, but yeah, the talks last week by Tadashi Takeda and I'm sorry, I can't read my own writing. Sabeda Matsumoto and Henry Sagerman were all wonderful examples of people doing things that allow the public and people to engage in math. But when you're giving a presentation, a talk, you kind of have an audience that doesn't really want to think hard about something. They want to experience math. And so here's something I've tried in public lectures that I thought gave an experience of math without requiring some sort of deep thinking. So maybe you've seen this before. If you have, just bear with me and I'll try to get through it quickly. But let's imagine we're going to play, we're involved in a game of Clue, only we're really in the rooms. And you're just supposed to pick one of the rooms. So I'll give you a minute to choose. That's enough time to choose a room. And then, and so now locate that room somewhere on this grid. So now here's the rule. The rooms are going to get destroyed, and you're trying not to be in the room that gets destroyed. And I'm going to give you a number, and you are going to move that number of rooms. You're just allowed to move up or down or right or left, but not diagonally. And we'll hope that you're not destroyed. So the first thing is to move 3. So if I was in the hall and I wanted to move 3, I might go 1, 2, 3, and find myself in the sunroom. You're allowed to go back, but so go ahead, move 3, and try not, if you get killed, try not to give it away.
You just said you're in the hall. You can move.
I'm in the hall. I could go study to the right, library up, sunroom. Yeah. Okay, so move 3, and hopefully you weren't in me in the sunroom. Okay, I'm dead. All right, so those of you still alive, move 5. All right. And hopefully you weren't in the dining room. If you were, try to keep your mouth shut. Okay, now move 1. And there goes whatever was next to the ballroom. Next, move 6. Yeah. All right, it's not that many rooms left. So now you're supposed to move 3. And then 4. So hopefully you weren't in the hall. Finally, move 5. Now there's 2 possibilities. You're either in the billiard room or the library, so you're either going to stay where you are or you're going to move, and I'll tell you to move. All right, so that leaves the billiard room. Let's see, there were 9 rooms. There's maybe 180 people in the room, so 1 out of 9 chance that you got it right. So that means about 20 people should still be alive. So if you're alive, raise your hand. So everybody's alive. Wow, that's amazing. Yeah, so this is something that magicians do. It was an old magic trick, and it's a little more dramatic if there's one person and everyone's rooting for that person. And in one version, it was routined as kind of the command from outer space, and the magician just pulled out a phonograph record, so it was clearly not interfering with what was going on, and it was some space voice, and the person was moving around, and they survived. When I was a kid, David Copperfield did this on TV. He had a bunch of cards, and you were supposed to run up and put your finger on the color TV screen, which kind of gave you more radiation than you were supposed to get in your life in those days, and trace it around, and every kid in the country survived. But one thing that it's always advertised as a magic trick, but it doesn't feel like magic. Does it feel like magic to you? It doesn't feel like magic, like, the magician's gone and then comes out of the whatever sitting over there. It doesn't feel like magic. It has a very different feel. And in public lectures, I've demonstrated this in various ways, and just asked people to focus on what that felt like. I mean, you feel like, in some sense, that the repertoire of phenomena you're experiencing is somehow regulated. It's regulated by some mechanism, and you're not quite sure what it is. And this is something, when we encounter this as mathematicians, we know there's something we can go to work on. We've experienced something mathematical. Maybe we've experienced an invariant, or we've experienced something that was unexpectedly regulated. And in this case, I'll just let you know, I started out with these 9 rooms, but instead of naming them after the rooms in Clue, let's just number them 1 to 9. And then if you were astute, you might have noticed that I didn't really give you 9 choices at the beginning. I gave you 5, and in fact, those were the odd numbers. So I started you out on an odd square. And if you move 1, you change parity. So when I said move 3, I knew you ended up on an even square, and I could take away any odd number, and on and on and on. So I could control where you were. There is an invariant you're experiencing, which is the parity of the number. Now you're going to have to excuse me because something went wrong with my, okay, that's back. Okay, yeah, so there was something wrong with the parity of the number. There's something going on with the parity. So that's one thing. That's one thing I think we mathematicians that I always kind of want to convey, that without having to think about something, there's math in all your experience. Whenever you have a sense that something isn't random, there's something else going on. So off the top of my head, there's only one other thing. There's another example I can think of that I've tried, and I couldn't get the props for it, so I'm going to show you a video of a different lecture where I demonstrated something that I feel is something else that you can use to convey an experience of mathematics. And so this was a talk at the when Milner got the Abel Prize, and I was trying to give an explanation of what it meant to have a 7-dimensional manifold that was homeomorphic but not diffeomorphic to the 7-sphere. So hopefully the sound here will work. Let's see. No. So, oops. So can I get sound? Is there a way to get sound on this? It should be there. Let me try again.
You can just lip sync.
Yeah. That's not. Yeah, I have HDMI on. I'm going to try one.
I don't know if this is really how things
It's
happen,
here.
but here's what I picture. So this is supposed to be a 7-sphere, and you can do things with it. You can twist it around, you can smush it, but you can't. If you do smooth things to it, you can't ultimately change the fact that it's round and it looks like a sphere. But if you allowed yourself to make more violent changes to it, if you allowed yourself to wrinkle it up and twist it and pull on it and wrinkle it and step on it, and this is what I imagine happened in 1956. You're stepping on it and twisting it, and you're making it really gross and dirty, and so you go to blow it up and smooth it out again. And you can see, by the time you straighten it out and smooth it back out again, you get a surface that has a completely different shape.
Okay, so that's an example where you show something that people realize is impossible. I mean, there's supposed to be a moment of astonishment there, but people realize something's impossible, and if you can engage them to think about it, how do you know that you can't turn a balloon into a donut? How do you know? Or how do mathematicians get organized to think about that? And that's something, I've used that to segue into a talk on the Euler characteristic or something like that. But already just freezing in that moment, saying, you think, everybody thinks that's impossible, but how do you know that's really impossible? That's a mathematical moment. What do mathematicians do to recognize, to say that that's impossible? I don't know if the word got out, but I kind of somehow got a reputation about being an expert on holes. And a few years ago, I got asked to be interviewed on some show. I don't know, I didn't get the job, but it was some show about holes. And I had a conversation like this. So suppose I dug a hole. Would you call that a hole? And I was like, well, it depends what you mean. It's a hole, like if I had an apple and a worm bored halfway through, I would call that a hole in the skin, but I wouldn't call it a hole in the apple. And they're like, so that wouldn't be a hole. And I'm like, no, well, what would be a hole? And I said, well, a tunnel's a hole. And they're saying, a tunnel? That goes sideways. You mean if I dug and dug and dug and dug and dug all day long and sweated and dug, you still wouldn't say I dug a hole? And at that point, I just said, I don't know. It depends on if you used your shovel or your talons. I don't know. So anyway, we get pigeonholed. Now, this instinct of ours to kind of grapple, to make precise abstract definitions, and to sort of understand the power of doing that, wasn't always a subject of ridicule. I mean, here's a picture of, this is Raphael's School of Athens that shows, well, in the back, Plato and Aristotle. We'll come back to this. But hanging at the gate of the School of Athens was the statement, let no one ignorant of geometry enter. Plato and the Greeks held mathematics and this kind of mathematical experience in enormously high esteem. I think I'm taking you on a little tour here. So that's Plato on the right, pointing to the sky, and Aristotle pointing more earthward. Plato had a very high ideal of this sense of mathematics. Plato, advocated that mathematicians were describing the entities in a world of divine forms, that the mathematics we look at exists eternally, and it's something that humans are discovering and encountering, but not something we're making up. In there's a picture of Pythagoras, and then over here Euclid, and it's an amazing thing, kind of going back and thinking about this aspiration of Plato and reading Euclid. And in fact, I didn't really, I studied geometry in high school, and I didn't really think critically about Euclid until just a few years ago, and I taught a class we have at Harvard in classical geometry. And to sit down and read Euclid and think about what Euclid was trying to get straight and how many years it took us to do it. I mean, it wasn't really until Hilbert that we had the foundations of geometry in a completely rigorous form. It really made the hairs on the back of my neck stand up. But I want to go into it because I've also there are many things in classical geometry that I found kind of that I found beautiful to try and explain to a lay audience. And this is something I talked about in a talk to a group of artists a few years ago. So here's one of my favorite constructions in Euclidean geometry. It's the construction, given a point in a circle, the construction of all circles through that point that are perpendicular to the circle you started with. So this is how you would, if you were working in the Poincaré disk model for hyperbolic geometry, this is this is how you would construct the lines. So I'll just go briefly through how you do that. You draw a line out to the side. You make a perpendicular. Well, I think I'll just show you the pictures, right? You construct what we call the inversion of that point in the line. Let me just do the pictures instead of explaining it. You construct this middle line, and then all the beautiful thing is that the family of lines that go through the point you started with that are perpendicular to the boundary, they all share a common center. And that's just one of many, many striking facts in classical Euclidean geometry. Now, what do you need to get straight if you're going to construct something like that and prove something like that? Well, you certainly have to know what a right angle is. And Euclid defines a right angle as one for which the angle on one side is the same as the angle on the other. Euclid doesn't really tell us how we're supposed to compare two angles that are in different places, but that's somehow left to your intuition. We also have to talk about a circle, which is all points at a same distance, or all points that are at the end of a segment of the same length. So being able to compare line segments in different places is something that's important. And those are also things that aren't really carefully explained in Euclid. And then we're talking about points and lines, and Euclid's definition of a point doesn't, even to a mathematician now, doesn't seem that something you could really work with. A point is that of which there is no part. I don't know. I wouldn't know how to test if something was a point or not. If I was an out-of-work actor, I might be a point. And a line is a length without breadth. Again, that's something, it leaves something to be desired, but nevertheless, in Euclid's geometry, it was the basis of what the subsequent reasoning was. But the main thing I hope that we need, and I hope I conveyed that earlier, is a way of taking a figure in one place and comparing it to a figure in a different place. What we now call Euclidean motions. And this is something that is not explicitly spelled out in Euclid, but many hundreds of years of subsequent thinking led us to understand that that was fundamental in geometry. Now, this problem of getting clear definitions of things like points and lines, that preoccupied mathematicians and philosophers for many hundreds of years. And here's Leibniz in 1715 saying something that I think is strikingly modern now, that if we're studying two objects in mathematics, we want to consider them the same as if they share every imaginable property in common. So that's an articulation already in the 1700s of something very modern. And with that in mind, this doesn't look too bad. I mean, if you could make sense of that which there is no part, you could talk about points. Or maybe well, anyway, let me move on. So this is, of course, as many of you know, in mathematics, this is articulated even more precisely by Klein's Erlanger program in the 1800s. And Klein says that we begin by specifying the motions. And then the only meaningful concepts that you have in geometry that you can talk about are those that are invariant under the motions. So we could begin Euclidean geometry by studying Euclidean motions, if we could specify those, and then things like length and angle, those are the numerical quantities that we have a right to talk about. And this frees us if we think of ourselves in Plato's aspiration that we're humans trying to understand some language of some divine Platonic world. This lets us put any human overlay, like a coordinate system, on what we're studying, as long as the things we come away talking about don't depend on that coordinate system, and that they are invariants of motions. So this sort of begs the question, where do the motions come from? So we certainly know, I mean, Euclidean motions are very beautiful, and we certainly have an idea of what they are. We know how to write them down now mathematically. But these were regarded as the obvious motions that we experience. Oh yeah, so I wanted to put this up as a kind of a palette cleanser. This is a sculpture by Anne Lilly, who's an artist I know, who makes these beautiful kinetic sculptures that, I mean, to me, these really capture this sense that there's something regulating that motion, as intricate as it is, that mathematical sense that there is really something at work. Well, we know it's conservation of energy and all that, but these are very striking sculptures. I don't want to take a lot of time. I'm going to move on to the next one. Let's see. No, it's not letting me do it. I promise I'm not selling these. This one, oh shit, dang, screwed my own joke up. All right, so just pretend you didn't see that. I don't know why that's not going. Let's see. For some reason, oh yeah. I'll just play this for a minute. There's also really really beautiful illustration of Euclidean motions. There's one view of this that's, yeah, that. I mean, the arms, they almost look like they're square dancing, right? Okay, so there are these Euclidean motions, right? They're the motions that for hundreds of years were kind of regarded as the motions of the natural world. Except, now that's the point of this, they aren't really the motions that we see. I mean, this is me, a selfie I took in Shanghai standing in front of the Oriental Pearl Tower. But that tower's huge. It's not coming out of my head. Those aren't the motions that we experience. And in fact, Hermann Weyl said this in a very beautiful way in the classical groups. He says, the mathematician unwilling to draw on any external truth will be inclined to take the view that any group whatsoever can be appointed as the group of motions. And I mean, so that's how one way mathematicians get closer to this Platonic ideal of experiencing something divine. As soon as we understand that there was a human choice in something, we try to consider it without that choice. So in this case, Weyl's saying, well, there's a group of motions, we should allow any group. And you might wonder, like, what is it like to experience the world if with a different group of motions? And of course, that's actually what you do experience. Imagine you're walking down the street and you see a building, and something looks kind of funny about it, and so you try to walk around the side. And what you see when you go around the side is that it wasn't really a building, it was just a building painted on a giant piece of wood. And now you're looking at it at a funny angle. And then you step up to it, but the wood falls down, and now you're looking at that picture. And so we actually have three different pictures of that same building. And those are the visual transformations we experience, the transformations of perspective, not the transformations not the Euclidean motions. And so our eye can reconcile those as the same picture. And this is something that also really strikes me about mathematics, that this idea that Euclidean motions were the motions of nature, that these are the notions of geometry, was just kind of accepted with complete authority for hundreds and hundreds of years, and yet it's wrong. It's just visibly wrong. Those are some kind of made-up transformations, but they aren't really what we see. And this is something I think something very important about mathematics. I mean, we'll take a mathematical abstraction and we will designate it as having supreme authority. And we'll use that abstraction over and over and over again. And then at some point, it no longer gives us joy, and we thank it for its service, and we discard it, and we move on to some other abstraction. We ascribe infinite authority to something, and we're willing to revoke it as soon as it's sort of not doing the thing that we want it to do. And I think this is, of course, what people make fun of us for. We'll decide these are the rules of some game, half and half is whole, and we'll dig in and we'll exaggerate our commitment to that authority. But none of us working mathematicians really do that. We try out an abstraction. If it isn't solving our problem, we'll seek some other one. I was thinking about this last week during this speaking slot. It was the group on equity, and they were talking about, I went in to learn about that, and there's a lot of thought about authority in our mathematical culture, whose voice gets heard, whose ideas are regarded as stronger. And I remember walking into that talk thinking, looking forward to hearing it, but thinking I was going to be hearing something that was about the society of mathematics and not so much about mathematics. And in it, I was thinking about my own talk and this idea that the relationship we have in mathematics with authority, with the authority of abstractions and ideas, it's that same authority. And it made me realize, if not in the mathematical community, where? I mean, we are we work with authority as our medium, in a way, as our own, it's our own currency. So this is something deep about math that I've also tried in various ways to convey, this sort of sense that something can seem right for 2,000 years, and then all of a sudden, mathematicians will decide that wasn't right. There's something else in this. Let me think. I think there was a story I was going to tell, but I lost it. So when I, as a mathematician, see Raphael's School of Athens, of course, I don't see the people at all. The first thing I look at is that floor. I mean, that's like amazing, the perspective on the floor and the perspective in the painting. And this is something I've always kind of wondered. I mean, perspective drawings, perspective in painting is sort of thought of as beginning with Brunelleschi in around 1400. And before that, you would have you'd have paintings that would have a tiled floor that looked like that. And I don't know if that was just how people depicted things, if people really saw differently back then, or if sort of the experience of looking at a piece of art was just something different. But to our eye, of course, that floor looks really wrong. Now, there's something about a tiled floor that and perspective drawing that I find really beautiful. In fact, what I like to say is most mathematicians aren't really Platonists. I don't know, maybe you are, but I don't think many of us really think there's another world out there that of pure form we're reaching for. But once in a while, you have an experience in mathematics that moves the needle. And this is one of my favorite ones. So suppose you want to make a tiled floor. You're supposed to start out with a tile, which is some shape, and you're supposed to make a bunch of them. That shape can be any shape that tiles. So let's say square. So you start out with some shape, and you have to manufacture a whole bunch of identical copies of that shape, and then you lay them next to each other, and you fill out the floor until you get something like this. But of course, we just saw a tiled floor is also something that exists in perspective. And when I look at that tiled floor, I don't see those all having the same shape. So in fact, how do you make a tiled floor in perspective? Well, you start with one tile, and that has two edges, two pairs of parallel edges. So one of them meets at the horizon at one point, the other at the other point, at another point. So there's 2 points specified on the horizon. And then there's a diagonal. That specifies a third point. And once you've got that data, there's now enough information. The phenomena is so regulated, there's enough information to perform in perspective exactly what the Euclidean motions were. So let me just zoom in. I know I want to make that tile to the left, and I can't guess where its edge is, but I know what the diagonal is, so I can fill that in. And now I know the upper left corner, and I know where it vanishes on the horizon, and so I get the next tile. And you just move along, and I get like that, and you get all 4 tiles. Now we have to go up to the next row, and there's a whole bunch